Hello everyone, in this video we are going to learn how to calculate the induced current in a conducting loop that is moving out of a static and uniform magnetic field. In this problem, the resistance of the loop is 1 ohm, the velocity is 2 meters per second, the length of the frame is 1 meter, the height of the frame is 0.1 meter, and the magnetic field is 1 Tesla. Next, we are going to sketch the time trace of the induced current. Consider that as long as the frame is entirely in the magnetic field, there is no change in the flux going through the loop. Therefore, there is no induced current either. Once the frame has entirely moved out of the magnetic field, again, there will not be any change of the magnetic flux. Therefore, there won't be any induced current either. We will only see an induced current while the frame is moving through the boundary of the magnetic field. Let's choose t0 to be the time when the frame first encounters the boundary. Then the current is going to be 0 all the way up to t0. Then it is going to jump up to some value for a limited time and then jumps back again to 0. The magnitude of this current can be calculated from Ohm's law, where epsilon is the electromotive force and R is the resistance of the loop. The electromotive force equals to the absolute value of the time derivative of the flux going through the loop, which is equal to A times B, where B is the magnetic field and A is the effective surface of the loop that has magnetic field in it. The surface can be expressed as the height of the frame multiplied by the effective length, which encounters magnetic field. This equals h times the velocity times time. This then tells us that the electromotive force can be expressed as the time derivative of the height multiplied by the magnetic field multiplied by the velocity and multiplied by time. When we take this derivative, the time will cancel, and therefore the electromotive force is simply the height times the velocity times the magnetic field. Plugging this into Ohm's law gives us that the current induced in this loop is going to be H times V times B over R. So height, velocity, magnetic field divided by the resistance of the loop. The time it takes for the frame to completely move through the surface equals the length of the frame divided by the velocity that the frame is moving with. In other words, delta t equals L, the length of the frame, divided by the velocity. Therefore, this delta t here equals L over V in seconds. Finally, we need to determine the direction of the current. Consider that initially the magnetic field is pointing into the board. As the frame is moving out of the magnetic field will still be pointing into the board, but now there is going to be less flux. This is equivalent with adding flux pointing out of the board, which is what the current wants to counteract by inducing a magnetic field pointing into the board. Using the right-hand rule, we can find that in order to produce a magnetic field that points into the board, the current must circulate clockwise in this circuit. Finally, let's highlight our results. The magnitude of the current is H times V times B divided by R. The time it takes to move through the boundary of the magnetic field is L over V, and the induced current in this circuit will circulate clockwise.